And today we are going to have a kickoff event where we're going to hear from a number of NASA speakers to fill your head with inspiration of all the different great things that students can do, and also give you, a teaser of some of the education resources we have coming up. So my name is Deanne Bell. I am the founder and CEO of Future Engineers. This is a NASA challenge, and Future Engineers is honored to be administering this challenge. And I will be with you every step of the way as your host and MC, and I am honored to pass it over to Bob Cabana. Bob Cabana is a former NASA astronaut. He currently serves as the agency's associate administrator, and he was formerly the director of NASA's Kennedy Space Center. So take it away, Bob.
Oh, thanks so much, Deanne, and thank you all for taking part in this awesome NASA TechRise Student Challenge. What a great thing for teachers and students alike. So, we got a lot of stuff going on at NASA, and I also have to thank the Department of Education, just like Deanne did, for allowing us to be part of this Ed Games Expo. Now, from a STEM point of view, NASA's STEM program is absolutely outstanding. We have so many resources for all of you to use in motivating those next STEM students out there, right, that are going to end up being engineers, and who knows, you might even end up being an astronaut one day. I never dreamed I could be an astronaut. I just wanted to fly jets when I was little, and I love math and engineering, but it's because of great teachers like all of you that instilled that in me when I was young, and it allowed me to have an awesome career and reach my dreams. Now, I got to get this right, so I'm going to read this, okay? I want all of you to make sure that you learn more about NASA STEM's program. I want you to go to nasa.gov/STEM, all right? nasa.gov/STEM, and I want you to subscribe to the NASA Express e-newsletter to stay informed on all the great stuff that we got going on, the STEM offerings for your schools and everything. You guys, we have so many resources, and I just know you're going to love them. There is so much going on at NASA. We got the Artemis program. We're going to the moon. We're going to put the first woman and the first person of color on the moon with the Artemis program. We got a big test flight coming up the end of this year with our crew. We're on Mars. That Perseverance rover with the Ingenuity helicopter, it is so dang cool. There are so many things that we're doing, and we can tie all that into your classroom too with great experiments for you to run. So NASA's STEM program, education programs are great. I want to thank you all for participating. And with that, I'm going to say goodbye, and I'm going to turn you over for this great video coming up. Thanks, everybody, for participating.
Thank you so much. And with that kickoff, we are going to show you a teaser video of our new NASA TechRise Student Challenge. So I'm going to go ahead and share my screen and share that video while we bring on another speaker from NASA headquarters. So here we go. And we're off.
Are you ready to build with NASA next year? NASA's launching a new technology challenge for schools. 6th to 12th grade students can either launch an experiment on a rocket or fly one on a balloon. What will you see? What will you change? What will you explore? Learn more and sign up now at futureengineers.org/NASA TechRise.
All right, and you guys are in for a treat. Not only do we have one person from NASA headquarters tuning in tonight, we also have another. So next, I'd like to introduce you to Jim Reuter. Jim Reuter is the Associate Administrator for the Space Technology Mission Directorate at NASA headquarters. He's been in this position since June 2019 and served in acting capacity since February 2017. And he provides executive leadership and management of the technology programs within STMD. And I'm very excited to turn it over to Jim to give some opening remarks. Thanks for joining us, Jim.
Well, thank you, Deanne. It's a pleasure to be here. It's really exciting. As Bob mentioned, I'm also honored to welcome you to the kickoff at this NASA TechRise Student Challenge. We're really excited to share what I think is an extremely exciting challenge with all of you. I hope you'll agree. TechRise offers students grades 6 through 12 the chance to design and build their own technology experiment. Then they can fly that experiment in suborbital space, just like NASA engineers, university researchers, companies, and so on. NASA uses, we like to use suborbital vehicles to test and mature technologies for future space exploration. You kind of go towards what's referred to as the edge of space, altitudes that replicate some of the conditions we'll see in space, such as microgravity, high altitude solar exposure, radiation, extreme temperatures and vacuum, and intense spacecraft vibrations. So by understanding in a suborbital, when it's relatively low cost, how the payloads respond, then they can confirm their designs and make refinements and improvements before they go into the more expensive and more challenging areas of space where they perform. And so researchers are often preparing their experiments for things like orbital deployments, small satellites on missions to the moon or Mars. And through TechRise, what we're going to try to do is have the students directly participate in that same process. So that can hopefully foster creativity and open their minds to the importance of testing when designing their experiments. But in order for this to be successful, we really need the support of the educators, you in this audience. So it's such a pleasure to be here for it. TechRise requires student teams to work with an educator as a mentor. At NASA, we absolutely know your guidance is critical. You're preparing our future skilled workforce and instilling in them core values like teamwork and ensuring equity among the participants. And with you, our educators, we want to support all students and welcome them to STEM, aerospace, and our growing community. So for the next 2 hours, you will learn from NASA subject matter experts in lunar exploration, in Mars exploration, climate research, imaging and remote sensing technologies, and microgravity research. I really ask you to ask questions along the way and consider how students can experiment with and test technologies and concepts across a wide range of topics. And you'll also hear in these 2 hours from fellow educators who supported student flight tests in the past to gain their insights and learn from this experience. So I especially want to thank the Department of Education for inviting us here at NASA and our partner, Future Engineers, to participate in these 21 Ed Games Expo. And thank you to the dedicated educators who are joining us today. I also want to thank our great NASA team that are pulling off this challenge, including our STEM engagement folks and Armstrong Flight Research Center, who runs the Flight Opportunities Program for us. A special shout out to Danielle McCulloch. So Deanne, back to you for an overview of the NASA TechRise Challenge.
Amazing. Thank you so much, Jim. Thank you to Jim and Bob for those great welcome remarks. So now I am going to dive into what is this challenge all about. So the NASA TechRise Student Challenge, right? We touched a little bit at the beginning, but I'm going to show some slides and I'm going to walk you through what this challenge is all about and what it's going to mean for you and your students to participate in this. Okay, so bear with me one more second while I share screens. I'm learning how to push lots of buttons in sync. So here we go. All right. And I'm gonna present. Okay. So, as you know, this is the name, NASA TechRise Student Challenge. And I'm first going to just dive into rockets and balloons. So when we think about this challenge, it's really kind of like two challenges in one, right? So we have this umbrella where students can propose an experiment to fly on a suborbital flight. But we've got two very different vehicles, right? So we've got rockets and we've got balloons. And the big thing to know is that the experiments, they're not going to be huge. They're going to fit in a box that's 4 inches by 4 inches by 8 inches. So it's kind of like two cubes stuck together, right? So you're thinking about that volume and what kind of experiment you can do in that volume. And when the students are thinking about what they want to propose for this challenge, you really need to think about what vehicle you're going to propose for, right? So we've got suborbital rockets that give you about 3 minutes of microgravity or 0G or weightlessness. So that's a really great opportunity for space exploration experiments. And I know that we're gonna go into more detail about this later. And then we've got the high altitude balloon, right? So we all know about balloons. Now this is a commercially operated balloon, and this experiment's gonna go up and it's gonna have at least 4 hours at 70,000 feet. So you can think about all the things you can see and all the things you can sense up there for your experiment. And in a nutshell, it means that it covers all kinds of areas of space exploration, from thinking about microgravity and thinking about developing experiments related to the moon or Mars, and also thinking about Earth science experiments as well, right? When we think about that balloon and how we can better understand our planet. So this challenge is open for U.S. schools. It's open for students attending 6th to 12th grade and at U.S. public, private, and charter schools. And when you put together a team to submit for this, it's a little different than some of our previous challenges. We need a team that has at least 4 students. There's no max. You can have as many as you want, but we need to have at least 4, and there needs to be 1 teacher or adult employee of the school attached to the team. And so when you think about like how you can participate with this, it could be your whole class that submits a proposal. It could be your whole grade. It could be an after-school technology club that you have. However you want to assemble a team within the students at that school, we welcome those ideas. And prizes, of course, it's a challenge, so we need to have awesome prizes. So we are excited that there are going to be 57 schools that are going to be selected to fly their experiments. And so as a winner, you're going to receive $1,500. You're also going to get a welcome kit inclusive of a flight box to build your experiment, and you're going to get an assigned spot to test your experiment on the vehicle that you submitted with your proposal. So either that suborbital rocket or that high altitude balloon. And these are NASA supported commercial suborbital flights. And so when we think about, well, what are these things exactly? Well, let's dive into it. We have 3 flight providers that are going to be operating the flights on this challenge. 2 are on the rocket side and 1 is on the balloon side. So we'll start with the balloon. We've got all those experiments for the high altitude balloon are going up on a Raven flight, and then we've also got 2 different suborbital rockets. We've got Up Aerospace and Blue Origin, and we are going to go into much more detail on that later on in this presentation. And I want to just make sure we illustrate the program dates. So the challenge launched last week, as you know, but that's really just planting the seed, letting it percolate in your head so that when we get to the next school year, we can start thinking about putting in those entries. So the entries are going to open August 18th, close November 3rd. We're going to judge all of these amazing entries, and then we're going to announce the winners January 21st. And then that's when the education journey begins of building those experiments, and we're going to be there every step of the way, helping you with curriculum, and we're going to launch those flights in early 2023. So the last thing I'll say is that in terms of participating in this challenge, the first step is putting in a proposal. You don't need to have ever flown anything before. You don't need to have ever coded before or done electronics before. You need to have that good idea, and you need to use our template, which we are going to be launching later this summer. Put in your experiment idea, upload it to our site, and that's how it all begins. And if you're selected, then you get the money and the funding and the assigned spot to go and build that experiment. So I'm going to go ahead and now tease up the next session of our TechRise kickoff event, which is hearing from NASA experts, right? So you're thinking, oh my gosh, you could do anything, space exploration, Earth science. So we're going to hear from experts related to exploring the moon, Mars, imaging, remote sensing, climate, microgravity research, and we're going to just fill your heads with inspiration from hearing about how NASA is conducting research in these different areas and how many of them have used flights to prove their technologies. So I'm going to go ahead and stop sharing screens here, and I am going to transition over to our very first speaker we have for our expert sessions tonight, which is Niki Werkheiser. I am so excited to introduce her. So Niki Werkheiser is the Director of Technology Maturation at NASA's Space Technology Mission Directorate. She brings a wealth of experience managing complex projects across NASA centers. She's built and managed the agency's in-space manufacturing efforts, including recycling and 3D printing in space. And now she's going to talk to us about all the exciting technologies in store for the moon. So Niki, I know I'm going to be sharing, I'm your co-pilot, right? I'm going to be sharing your slides.
Yes.
All right. I told you I'm getting good at these buttons. I'm going to share the screen and get your slides up. So bear with me 1 second.
Fantastic. Can you hear me okay? Just making sure.
I can, loud and clear. All right, here we go. Just tell me when I need to press next.
Will do, and thank you very much. Okay, good afternoon, everyone, and thank you for having me today. I am absolutely thrilled to be here to share some of our exciting activities underway for our lunar surface technology development. and how there's a real opportunity here to test some of these technologies on suborbital flights and put us one step closer to the moon. So Deanne, if we go to the next slide. So as I'm sure everyone here knows, these first steps on the moon took place on July 20th of 1969, and December of 1972 was the last time the Apollo was on the surface. So that means that anyone really under the age of 50 or so has never seen a human walk on the surface of the moon. I just happen to be in that category, just barely, but I'm there. So I'm eager for us to go back, and when we do, we really want to stay. But in order to do that, we're going to need some very special technologies, and I'm going to talk to you today about some of those that we're developing now and how we're using suborbital flights to help us get there. So if we go to the next slide. So I work in the Space Technology Directorate at NASA with Jim Reuter, who you heard from earlier as our fierce leader. And our mantra is technology drives exploration. And our programs are actually aligned along what we call the technology readiness level spectrum, starting with the low TRL, that's our early stage innovation programs. And those really focus more on R&D and primarily engage with universities across the nation. Then we have our mid TRL areas, which is technology maturation, which is admittedly, I'm a little biased. I'm the director for that area. And this is my favorite part of tech dev. Let's see here, I got a message there. It's my favorite part of tech dev because really it can be seen kind of as the bridge between that R&D and early stage and then mission or commercial infusion. So we get to work really across all of those stakeholders and to take those initial concepts to prototypes. And then finally, the end goal, of course, is to evolve high TRL technologies led out of our technology demonstration missions program. So this area really works more with industry and engineering implementation into our NASA missions as well as commercial infusion. So in 2019, shortly after the Artemis program was announced, the Lunar Surface Innovation Initiative was created. LSI works across industry, academia, and government to develop the transformative technologies that we're going to need for lunar surface exploration. So I'll be focusing on those today. Some of the key technologies include mitigating lunar dust, excavating and extracting the in situ resources on the surface for consumables production and construction, and then obtaining access to different locations on the moon, some of which can be quite dangerous for humans to explore. So we use robotic scouts, for example. And then, of course, for all of these, we have to survive the harsh environments of the moon. So as you might imagine, in order to ensure that we are developing the types of capabilities to live and operate on the moon, we really have to utilize the different types of flight opportunities out there to inform these key technology developments, especially when you're talking about novel technologies. So this includes suborbital flights, as well as our early commercial lunar payload services missions, which take us all the way to the moon. So Deanne, if we go to the next slide. So how do suborbital flights help us get to the moon? Well, as Jim mentioned, NASA uses suborbital vehicles to test and mature technologies for future space exploration. So by understanding how these payloads respond to the unique conditions, researchers are able to confirm their designs and then make the necessary refinements and improvements before we send them all the way to the moon, which can be really expensive and even more challenging. So for the technologies that we're developing as part of the Lunar Surface Innovation Initiative, in some cases, we have very fundamental questions that we really need to answer before we send that demonstration all the way to the moon and even one day Mars. So through TechRise, students are able to directly participate in this same process. Obviously, this can really foster creativity and open their minds to the importance of testing when designing experiments. And to be honest, we get some really exciting ideas from students that sometimes even NASA engineers don't think about. But in order to be successful, we really need support of you, the educators. So for me, this is a really fun topic. I could go on and on about all the different areas we're using suborbital flights and different testing platforms. But in the interest of time, I've selected a few key areas I'd like to use as examples today of how we're using those suborbital flights, including one that actually spins the cabin to create to recreate the moon's 1/6 G environment. So if we go to the next slide, I'll talk a little about those. So first, let's talk about lunar dust mitigation. There's a good reason that we call this dust mitigation rather than dust solutions. Dust issues are very real and they have impacts or effects on pretty much every single thing we do on the surface. So for example, during the Apollo 17 mission, crew members Jack Schmitt and Gene Cernan, they had trouble moving their arms during the moonwalks because the dust had really gummed up the joints, and it was so abrasive that it actually wore through 3 layers of the Kevlar-like material on Jack's boot. So we actually have current technologies under development that use active, passive, and operational measures to address dust mitigation. Examples of some of these that are underway that will be demonstrated on suborbital flights before being tested on the moon include one that's called low-G transport of dust liberated from spacesuit fabric. This lunar dust contamination that's in the cabin environment after every EVA is really inevitable. So this demonstration contains a little mechanism called a cloth bot, and it has a DC motor with an arm that holds fabric with simulated dust particles. And so it shakes the fabric to see what sticks and what doesn't. So it directly supports the modeling efforts that are under early stage innovation projects. And I like this example because it's quite a simple mechanism, but the truth is that without recreating that 1/6 lunar G, there's really no other way to get this fundamental information and to compare it to the models that we're doing to see if we're on the right path, right? The next experiment will actually improve our understanding of electrostatic dust charging and lofting. It will compare the low G results in the suborbital flight, where we spin the cabin to create that 1/6 G, to the charging and lofting model that's currently under development through our NASA early stage innovation project. And then we have another one. It's called Hermes Lunar G, and it's a suborbital demonstration that leverages previously flown ISS flight hardware. So they've already flown this on ISS, and they got data on how the particles act in micro G on space station. This one will now look at how dust particles settle in the lunar G environment, and then compare that data to micro G. So there will be 4 tubes laid out with a number of different dust experiments, including some for dust settling, size sorting, and granular mechanics. So all of this is going to provide key answers to characterizing how dust behaves in the lunar G environment and help inform those CLPS payloads that I mentioned earlier that will go all the way to the moon. So if we go to the next slide, I'm going to talk a little bit about in situ resource utilization, or ISRU. This focuses on how we're going to use the resources on the moon's surface to get consumables for the astronauts and propellants for our rockets, and then how we can use those same resources in conjunction with additive construction techniques and excavation technologies to build structures like landing pads and possibly even habitats. And many of these technologies actually feed forward to Mars as well. So a couple examples of suborbital demonstrations for ISRU include our vibratory lunar regolith conveyor. This is a granular material transport system demonstration. It studies the vertical transport of those lunar regolith simulants in vacuum under that reduced gravity environment. So it contains 2 sets of conveyors that will test vibration on different types of simulants. And this really helps raise that technology readiness level I was talking about to a 6, and it buys down risk before we actually have these demonstrations on the lunar surface. Another example is called the electrodynamic conveyor. This would actually provide NASA lunar surface operations like ISRU and construction power alternative to the state-of-art conveying technology. So EDC technology could be more reliable for long-duration missions due to a reduction of moving parts, and the experimental EDC involves what they call a reduster component that allows the repeated testing of regolith transport from shallow beds of the regolith. And this one's in conjunction with the University of Central Florida. Now, if we go to the next slide, I just wanted to give an example of one of our CLPS payloads that all of these suborbital demos help to inform. Our first one is an ISRU demonstration. Demonstrations called the Polar Resources Ice Mining Experiment, or PRIME. You heard me mention how ISRU is extremely important because when we're so far from home, we simply have to be able to use the local resources for our consumables. It was discovered that there's a lot of water at the moon's poles. Even some of the most conservative estimates suggest millions of metric tons there. And that water, as I mentioned, is really critical for mission consumables. So Prime 1 will fly on an Intuitive Machines CLPS lander to the lunar South Pole in late 2022, and it will assess the volatiles and determine water content. And this demo consists of 2 high TRL instruments. One is a mass spectrometer, and the other one is a drill called Trident. And these same components will actually are common technologies that will also be used in the Science Mission Directorate's Volatiles Investigating Polar Exploration Rover, thank goodness for acronyms, right, or VIPER mission. So testing these on the moon will help to test for VIPER before it goes. And VIPER will actually add a rover as well to the mass spec and to the drill. And that will fly to the moon in late 2023. So you can see how these different test opportunities inform one another. We have the early suborbital flights that I talked about. All of those help to inform this type of prime mission, which goes to the moon early. Then prime helps to inform VIPER, which then adds a rover. So all these lessons learned, we kind of build on one another to buy down risk and to develop a technology. So if we go to the next slide, I was going to talk a little bit about excavation and construction. So excavation and construction is really kind of a bridge between ISRU, or excavation is a bridge between ISRU and construction, as it's required for drilling as well as for digging into the regolith to extract resources and to gather up some of that same regolith material to be used for construction. So construction using the moon's resources will be needed to provide landing pads as well as protection of crew members, hardware, and electronics on the surface. So this is an area where we have a great deal of industry and university involvement. For both of these areas, we're leveraging and learning a lot from companies that actually do these things terrestrially, as well as those who want to do it in space. And we're working with a great deal of universities to understand those regolith properties that I've talked about in those suborbital demos, and even to make the lunar simulants, the fake moon dirt, if you will, that we can use to test the hardware here on Earth before it flies. But there are many challenges and there are differences that we're working through. For example, excavation technologies will need to be lightweight, yet capable of digging in a reduced gravity environment. And large-scale construction systems really have to be autonomous and equipped to work without astronauts' help on the moon. So for all these systems, working reliably in these extreme environments is particularly challenging. A couple of experiments we'll be testing on suborbital flights include one that's called Dune Flow, which is just a great name, right? And this suborbital demo addresses the flowability of lunar regolith. It pushes the simulant through and extrudes, testing the stability of artificial slopes that are constructed in lunar surface material. So they actually use that regolith, and this one is actually slated to have an actual Apollo sample as well as different regolith simulants to guide the development of more accurate geotechnical or mechanical simulants for excavation and construction testing. And it uses
And Niki, I'm going to chime in. I think we're going to have to button up soon. And I know you were talking about autonomous testing and everything, which I'm super excited for kids to be doing that in space. So I just want to give you a heads up that
good deal.
We need to go to the next speaker. Cool.
And we can go on to the next one. Actually, if you just flip to the last slide, the others in between here are just examples of how we're using some of those suborbital demonstrations. Awesome. So flip to the very last one. And I just wanted to say this is just a quick snapshot of all of our different planned CLIPS demonstrations, several of which we'll be using those suborbital flights to test before they fly, as I discussed. And I just can't wait to see what the TechRise students will propose that we test next. And that's it for me.
I love that last image, and I love the idea of students coming up with experiments to fly on these suborbital flights that are proving ground for technologies that can go on to the moon. We're going back to the moon. It's so exciting, and you know, there's all kinds of technologies that need to be developed related to lunar exploration. And now we're going to pivot and go in a totally different direction. And we're going to talk about imagery and remote sensing. And we have a really great next guest. We've got Rodney Grubbs. Thanks for joining us, Rodney. So Rodney began his career as a co-op motion picture photographer at NASA's Marshall Space Flight Center, and he's currently the NASA Imagery Experts Program Manager and chairs the International Space Agency Imagery Standards Group. I can't think of a better person to talk about imaging from a balloon. So take it away, Rodney. I'm excited to hear what you got for us.
Great. I hope you can hear me okay.
And I'm going to share your slides as well. Is that correct?
Great. Thank you.
All right. Let's bring them up.
All righty. So I was very excited about this opportunity to talk to educators. My father was an educator, and my sister was an educator and a principal. My sister-in-law is an educator and a principal. So I've been around educators my whole life. So I hope everybody's having a great time today. And it's a pleasure to speak to everybody. So when I was thinking about this topic, I was thinking about, for some reason, I kept coming back to scouting ahead. You know, how do we use imagery to look beyond the horizon, what we can't see with our own eyes? Remote sensing is allowing us to take a peek before we're able to put human eyes on something. So think about the wagon trains heading west. They would send scouts out ahead to look at what's beyond the horizon. And they didn't have cameras back then, so they would come back and give a verbal account of what they saw, what was ahead, what was over the next rim, right? I can only imagine, I know they didn't have wagon trains probably in Arizona and Utah, but can you imagine if you were the scout trying to explain the Grand Canyon and telling everybody you're going to have to turn around, this isn't going to work, right? So that's kind of the way I want how we might be technology to scout ahead, to look ahead beyond the rim and the horizon. Next slide, please. So early in my career, we had the technology to freeze video and turn it into pictures. And this is a long, long time ago, a really long time ago. And there was a scientist who had spoken to pilots who had said that they had seen lightning in space, going out into space. And so he got permission to turn the video cameras on during space shuttle missions and to shoot video of the night side of the Earth, of thunderstorms. And he would come into my lab after a mission and have me freeze these little video frames. And the technology was very poor. We didn't have all these GoPro cameras and things like this back then. And he would have me freeze a frame of video that he felt showed lightning going into space. And he would do these research papers about, I believe lightning shoots out into space, not just to the ground. And at first he was met with a great deal of skepticism, but over time the technology got a little bit better, and now we know these things as jets and sprites. So this is an image of what these things are and what they look like over a thunderstorm shooting out into space. This was shot from the International Space Station. So just in my short lifetime, we've gone from a phenomenon that nobody knew about, but had only heard about from pilots looking over the rim, seeing the tops of clouds and during thunderstorms, and saying, hey, something is shooting out into space. And then the technology got better. And then they were able to finally accept that, yes, these things do exist. And now if you go out on Google and Google jets and sprites, lightning in space, you'll see images like this. So it was these crude cameras and verbal explanations of things that were able to lead to this discovery. Next chart, please. So imaging allows us to see things that we can see with the human eye in a different way. These are images of the aurora and cities at night, and the hue of that thin little atmospheric layer that protects us all, right? And so as we think about imaging and remote sensing, these kinds of things, these kinds of images should prove to inspire the next generation. And maybe there are other phenomena out there that are not yet explained, and we don't yet have the technology to see it as clearly. Just like in my short career, my short lifetime relative to humanity anyway, we've gone from seeing these sprites to them being acknowledged as being accepted technology. And so as you look at opportunities for perhaps to put an imager on a balloon or on a sounding rocket, maybe there are other phenomena that scientists are insisting exist out there that a camera at high altitude might be able to take just a single frame from, that might prove to actually be real, something that is scientific and unknown. Next slide, please. So one of the things that's cool about NASA is, you know, we go one step further and beyond our imaginations, right? So we have drones on Earth. Why not have one on Mars? And so some of you may have been following the Ingenuity helicopter. You know, it's not audacious enough that we land something the size of a mini rover or Mini Cooper on Mars, but we fly a drone and do those kinds of crazy things and take images of that. And this is just the beginning. And so the engineers and scientists that dreamed this up were the students of yesterday. And so what are the students of today going to do in just another generation or so? And it's the imagery like from a drone like this. There's no telling what we're going to find out before we humans go to Mars. And this is just the beginning. I can only imagine what the current crop of young people who are used to video games and all this technology and playing games with people all over the world, seeing and hearing all of that, what are they going to come up with if properly inspired? The last generation came up with this, which is pretty amazing. The mind just boggles at what the next generation might do. And it's imagery like this that tends to inspire people. You know, I definitely, obviously, I'm an imagery guy. I'm a big believer in it, and I feel like data is very important. But if we can just see it, and just you might see something that you didn't expect, right? Those are the kinds of things that might inspire the next generation of explorers. I can't remember if I have one more chart or not. Do I? Is that it?
No,
that's
it.
That's it. Okay. All righty. So I know that was short and sweet and maybe got you back on schedule here, but just think about that. We're trying to take that peek over the horizon, and imagery and cameras allow us that look, and you just never know what you might find, but you've got to go looking.
Yeah, and I think it's important to note that, you know, we're talking about imaging out to space, and you know, obviously we've seen so much great imagery coming out of Mars, but that has to start somewhere, right? And you think about all those people that developed that started when they were in high school taking pictures. And think about this. It can start with your students taking a picture from a balloon down to Earth and thinking about, what do I want to see? Is it in the visible spectrum? Is it not in the visible spectrum? Do I want to compare it to what was here before so I learn something from it? Like, what is in exactly what you said, Rodney? A picture is like 1,000 words, right? There's a famous phrase that I'm not saying properly right now. but yeah, I think there's so much opportunity for students to think about what they want to see and what imagery they want to take in these experiments. So thank you, Rodney, for sharing your insight. And now we're going to go to another possible area of thinking about what kind of experiments to develop. And this time we're going to talk about climate. And so we've got a really special speaker today. We have Alejandro Mundo. So Alejandro is an educator. He is a teacher in the Bronx. At a public school at the Kingsbridge International High School, a public school in the Bronx. And Alejandro is part of the NASA CCRI teacher program, and he's an associate researcher, which is a program which pairs teachers with researchers to conduct research. And so you've been getting your hands dirty, I know, doing climate research, and are excited about the prospect of students, you know, gathering data related to climate. So I'm going to pass it over to you, Alejandro, just to share a little bit about your journey, you know, with climate research, and then also engaging students with that as well.
Definitely. Well, thank you so much for Deanne. I really appreciate it. And hello, and thanks lots to everybody who's joining today. I'm super excited to be here and just being able to be part of this, especially lots of excitement, incredible this world. I'm so thrilled to be here with you, and just send a big shout out to all of the students, educators, scientists, and just everybody joining today. So glad to have you here. So my name is Alejandro Mundo, and let me tell you about myself. So I'm a geophysicist and earth science educator, and some of my hobbies actually include to just traveling, hiking, camping, so baking, stargazing. So I guess it's also good to say that I'm an outdoors, right, individual. I'm currently involved, like you were saying, at NASA Goddard Institute for Space Studies, known as NASA GIS. And I'm an educator and associate researcher there. And I also lead the science department and teach science at Kingsbridge International High School in the Bronx, New York City. So shout out to colleagues joining us from these communities as well. Ever since I was a boy, I found passion towards the outside world. Like I had a passion not only for nature, but on how things worked. As I grew up, like you can see on the pictures here on the left, I discovered that science was actually a passion within me. So thanks to role models who inspire minority students like me to do science, I decided that to pursue a career in STEM that would focus on the geological sciences and how the earth formed, how it functioned. So I went to college, I got my degree, and I continued to get involved in scientific experiences, visiting like Yellowstone Geyser, as seen here on the left. But then I wanted to dive in closer. So I got a master's degree in earth science education at the American Museum of Natural History, because I mean, informal learning has been and will continue to be a place of discovery and success as well for all individuals wanting to encounter science. But I discovered I wanted to do more than just science. So I wanted to also inspire, motivate, and just fuel that passion to younger and future generations about the power of discovery, exploration, and especially making sure that students from all backgrounds would get access to role models in STEM like me. So I became an educator, but even though that I've been involved in research and in the classroom, I have also been part of doing some research which, for example, if it's, you can see here on the images, whether if it's like learning about the metamorphism rate of formation in Manhattan, or finding some fossils that you can see in the image here, or being involved in climate research, as an educator, I wanted to pass on these experiences in the classroom that would last forever and just create that impact by role models through inquiry-based models. So let me just tell you here, for example, I've been as an educator for 4 years in New York City. Also, this is my second year, as you were saying, at Climate Change Research Initiative. And I'm so happy to tell you that I just published this STEM unit plan on climate change as of this year. So let me tell you a bit about the background here at the school where I am. This is in Bronx, New York. I teach earth science, astronomy, to juniors, seniors. It's a small school, but we got students from a Title I school, which includes almost 100% of low-income families, where it's a very diverse background, which involves about 90% of Hispanics, but also we got some other groups like Asian, Black, which is like 3%, and of course, white as well. So even though that we are a population of minorities, we have made it to the news. And just like I think it just connects to the previous presentation, because we have made it to the news where we get to send our names on the NASA Mars rover Perseverance, together with this opportunity that opened up to others. And so we decided to take that challenge. We sent our names. We were part of this opportunity, and we made it through different local channels like Bronx 12, Pix 11, the United Federation of Teachers, as well as even NBC, highlighting the stories of our students, minority students, who actually have made it and decided and have been part of scientific discovery and research opportunities where we are in their backgrounds, even if they are new to the country, because these are newcomers that have arrived to the country within a few months to a few just very recent, probably 1 to 2 years. But let me tell you about the Goddard Institute for Space Studies. So this is a climate change research initiative. This is a lab from the Goddard Space Flight Center, located in New York City, which has the research in exoplanets, astrobiology, but also climate change. So focusing on the last one, the Office of STEM Engagement at NASA GIS actually runs this program, which is the Climate Change Research Initiative. This is actually an incredible model because it focuses on having a scientist like Dr. Christian Brannon, my mentor, also grad students, an educator, and later during summer, the undergrad and also high school student join. And this is, as you can see, the levels of education are all together. It involves a vertical model that affects every single aspect of educator. And eventually, I also developed an applied research STEM curriculum portfolio. So here's a picture, for example, of our recent group where we have all of this part of our individuals. Also, we eventually leads into the research aspect that is then put into a paper, scientific poster as well. This one was actually about our research during last summer and was presented at the American Meteorological Society. Also, some part of the research was presented at American Geophysical Union. So it has been such a great opportunity to not just do research at GIS, CCRI, but also being able to transport it and move on. Let me tell you a little bit more about that research. So our goal is actually to use the Earth observations to inform urban planning efforts in order to mitigate the impacts of climate change in cities. It actually focuses on this phenomenon, which is known as the urban heat island. And this phenomenon pretty much says that in locations such as like big cities and like urban settings, pretty much downtown in big cities, the temperature for like the land surface temperature is actually higher than in other localities like urban or rural. And that's because of the materials, the buildings, and everything that it acts like a black body. And those temperatures would actually be trapped and create what we call the urban heat islands. So how do we actually keep track of them? Although you can go outside and get some temperature with thermometers, we actually have this satellite. So we use satellite imagery, for example, Landsat 8, which is about the distance between the Earth and the Sun is about 150,000 kilometers. We use Landsat 8, as you can see here, which is it goes around and gives orbit. So every 99 minutes, it goes around, moving at about 20,350 kilometers per hour. And Landsat 8 captures about 185 kilometers per SWAT. So eventually, I imagine it's going around, going different orbits and just traveling thousands and millions of kilometers in a 16-day cycle. The idea is that within this 16 days, we will have the whole Earth. It's actually going to be every 16 days, we got the whole Earth tracked. And eventually we can get, for example, land surface temperatures, which by the way, we're looking forward to the release of Landsat 9, which is actually happening on just fall of 2021. But when we have this imagery from satellites, we actually use bands like 10, 4, and 5, where using 10, converting radians from those images from at satellite brightness, and also we calculate the normalized vegetation index, which pretty much measures the vegetation health and the density. Then to lead some calculation of the emissivity. And when you calculate all of those and put them together, you get something that it's like the final land surface temperature. And if we know the land surface temperature, for example, for the past, but also we can do some models for the future. And we get this imagery from Earth Explorer, but then we bring it into ArcGIS. And we create some masks. For example, we got this mask from Landsat, and then we get into we can predict, and we can put the vegetation index as well as the land surface temperature map. And once we have this, we can actually run variables like of interest, such as the mean, the median, the trend, just percentiles as a whole. So here, for example, we got some percentile ranges, and we can focus on different aspects. So for example, the lowest ones, and we can create some type of maps. So whether if we want a true color image, or we also want the 80th percentile that gives us the urban coverage, or we want the 50th percentile, which gives us the green spaces or the land surface temperatures. That's the focus that we have been wanting to do, that can give us one of these land surface temperatures. So this, for example, from Durban, South Africa, which helps to identify just the land surface temperatures. So this actually, I brought it into a curriculum which has 4 different lessons. So a unit plan that focuses on climate change, remote sensing, the urban heat island, as well as land surface temperatures. And I'm actually happy to tell you, you were asking about how students actually get involved. Students have been able to go outside, even in pandemic times, by the way, to go out there and just be getting some through this infrared thermometers and getting data from whether like different materials, whether if it's like vegetated area or cement and other locations, and they get
yeah,
data.
and I love
example.
this. I'm gonna have to cut you short a little bit, but I think what you're talking about is exactly what we're talking about, which is inspiring awesome teacher like yourself, engaging students in this kind of research, but then as well, like, how do we take this? How do we take the idea of Landsat data and bring it back to how students can engage, right? And you saw them starting there with taking temperature on the sidewalk, but then how do we take that even higher? Like, how do we take that to the next level, right? And thinking about high altitude balloons and how you can, collect data in the atmosphere and collect imagery and tell a lot of these stories that you're telling, right? So I'm sorry to cut you off, but I wanted to just give you a little, like, 30-second timer. So keep going and we'll wrap it up and go to the next speaker.
Well, sure, definitely. So eventually this leads into data, like you're saying, and the analysis of data is such importance. So as we conclude in this, because like it creates some modeling as well, I do want to say that, after all, if you're a student, I want to encourage you to keep up building on the bright future that you have ahead of you. And also for educators, that let's continue to inspire our younger generation of scientists to continue to move at more diverse STEM fields and provide these opportunities of doing data and analysis, and just the generation of explorers in our world to continue to do scientific discoveries and take science action to impact our planet and beyond. Thank you.
Thank you so much, Alejandro. All right, great. Thank you so much. And we are next. We're going to change it up. We were originally going to go to George, but next we're going to go to Swati. And I'm so excited to introduce you to Swati. We've been talking about what experiments could you make for climate? What experiments could you make for imaging, for the moon? And Mars is a big one. So we have Swati, and she's kind of famous. You might have seen her at the Perseverance landing. So I'm going to go ahead and introduce you to Swati. Swati is the Guidance Navigation Control Systems Engineering Group Supervisor at NASA JPL. She joined JPL in 2004 after completing her BS in Cornell and mechanical and aerospace, and has worked on a number of different programs, including a flight to develop navigation systems for Mars, I'm told. So I'm excited to hear all about it, Swati. So go ahead and inspire us about how to design for Mars.
Hi, everyone. I'm super excited to be here. So today I'm going to tell you a little bit about the piece of the Perseverance rover that I worked on over the past 8 years. And it's super cool because although you may have seen a lot of the videos from the landing, you kind of never really feel what we did over the last 8 years to actually get to that point. So back in 2013, when I joined the project, we were given a task and they said, okay, you have to fly in 2020 and land in 2021, and we want you to reuse as much of Curiosity as you can. So just build it to print and you should be fine. The problem came with that Perseverance has a new science objective from Curiosity, and in order to do that, to be the first rover to seek the signs of past life, the community and the engineering community decided to send Perseverance to Jezero Crater, which was a much more hazardous place than Curiosity went to. So in order to actually land safely at Jezero Crater, we needed a brand new technology that would actually let us land safely. And to do this, we had to actually be able to see where we were coming down as we were doing the entry, descent, and landing. So all previous missions to Mars have actually used radar to basically feel where they were going and to kind of close their eyes and touch the ground. Once they felt where they were, they would stop. But for Perseverance, we added a brand new technology called terrain relative navigation. Now, what terrain relative navigation allows us to do is actually land with the eyes open. So as we're coming down on the parachute, we're actually taking images of the ground with the lander vision system camera. And by taking these images and comparing it to a map that we've created and loaded on board, we can compare the images to the map and orient them to figure out where we are with respect to the Martian surface. Once we know where we are, we're able to look down and we have another map called the Safe Targets map, and we find, given where we are, where can we get to on the Safe Targets map, and what's the safest spot in that region that we can get to that we can land in. This allows us to go to Jezero Crater, which is filled with cliffs and rocks, and actually see them as we're landing and be able to pick a spot in between all the cliffs and rocks and slopes and sand pits and land exactly where we want to land. Now, the super challenging thing about entry, descent, and landing is that there is absolutely no way to test the whole thing here on Earth. So we have to break it down into pieces. So we try to test like we fly and test all the different things that we're worried about. And we have 3 different ways that we do this. So the first one is using simulations and analysis. We run software simulations that model the environment in order to figure out what we think is going to happen. And this allows us to span all sorts of scenarios, you know, a really windy day on Mars, a very sunny day on Mars. What if it's, you know, landing on this part right over the cliff? What if it's going to land on this part? And by spreading the space around and running lots and lots and lots, like tens and hundreds of thousands of runs, we're able to kind of see all the different scenarios, including the very corner cases, off-nominal scenarios. The second aspect is hardware testing. You know, we have mock-ups of all these hardwares in our lab. We hook them up together and turn them on and run the software through them and feed inputs to have them pretend like they are in Mars and make sure that the computer doesn't reset, make sure that it can actually do all the processing fast enough for what we needed to do on Mars on landing day. The third aspect is field testing. So this is where we take real hardware, the mock-ups for the real hardware, and we put it into a representative environment in order to really validate what we're doing. Because, you know, we can design tests, we can think of things, but at the end of the day, the other two, the simulation, the hardware testing, are only as good as we can imagine them to be. What field testing allows us to do is to actually put it in a real world scenario where we can't control all the variables and see if the system that we designed can handle the real world when we're not actually able to control all the different things. This allows us to say that even if we haven't thought of something, even if we haven't designed specifically with that particular thing in mind, that we've built a system that's robust enough to make it through in a real world scenario. So all of these 3 different aspects are called the V&V trifecta. We use all of these during the development in order to piece together the lander vision system as part of the terrain relative navigation. So I wanted to give 2 stories and share with you about how this really helped us to get to landing day successfully. So the first one is on this hardware testing blue box down here. So we had a simulation mock-up that we had inherited from Curiosity, and it was capable of doing the full Curiosity end-to-end entry, descent, and landing simulation on the hardware at JPL. Now, in order to really show that Perseverance could land, though, we had to add terrain relative navigation. And this involved integrating the whole new computer into the existing system, hooking them up so all the new computer is talking to the old computer, it's saying the right things. We needed the new aspect of the simulation to actually real-time render the images of what it would look like as it was descending, to feed that to the lander vision system so it could pretend that it was actually seeing the descent on Mars. And we went back and forth, and we're trying to get all these pieces together. And it's not working, and it's not working because we're trying to build it up incrementally, because we're first testing this piece, and we're first testing the next layer and the next layer. And eventually we got to one layer and it wasn't working. Spent weeks trying to figure out why it wasn't working, and couldn't get past it. We kept, the simulation kept showing the rover crashing because it couldn't figure out where it was. So in the end, we decided to skip a few steps and see that if we just went to the whole entry, descent, and landing and didn't have the steps in between, because each step had its own assumptions, it had its own interfaces that weren't necessarily the final one, would we find something? Would we find that maybe that bug was just associated with that level? So we gave it our go, where we just said, okay, let's just see if it's working enough that we can do the whole thing. And we tried it, and it landed on our on our attempt. So after a month or 2 months of trying incrementally, fixing all the bugs, getting to block and then like jumping a step, we were actually able to get it to work. And about a week before the Christmas holiday break. So that was our first time that Perseverance landed in any form, whether simulated or real. And this was back in the winter of 2018. So that was our first glimpse that, yes, we could potentially actually do this on Mars. So after this, we learned from these mistakes, learned from the bugs and the testing, and then we created a mock-up of the lander vision system that we flew out in the Mojave Desert in order to get that real world aspect to the testing, to be able to be sure that whatever we had designed, we knew that it would work. So I'm going to play a little video here that describes our field testing for Mars 2020 terrain relative navigation, why we took it into the desert, what we learned from that testing, and then how it relates to Perseverance's end goal.
We are in Death Valley testing terrain relative navigation, the new technology for Mars 2020. The terrain in Death Valley is very much like Mars. It has a lot of sand dunes and steep slopes. It's quite similar to the landing site that Mars 2020 will be going to. We're taking a copy of the system that will be on the spacecraft, and we're testing it in the way that it would be used during the flight mission.
Terrain relative navigation gives the vehicle the ability to figure out where it is. This is kind of along the same lines of what the Apollo astronauts did with people in the loop back in the day. Those guys were looking out the window and looking for different craters and other features on the moon that they knew of from the maps we had of the moon. So that way they could figure out where they are and figure out where they needed to land to be safe. So for the first time here on Mars, we're automating that.
What terrain relative navigation gives you is the ability to avoid hazards that you already know about. So large hazards, hills, craters, things that you've seen before. With the camera, we take images as we're descending, and we match pieces of the image to orbital imagery that we have stored on board. And if we make many of these matches, we're able to figure out where we are relative to the map.
If we didn't have terrain relative navigation, the probability of landing safely at Jezero Crater is about 80 to 85%. But with Mars 2020, we can actually bring that probability of success of landing safely at Jezero Crater all the way up to 99% safe every single time.
We don't have an astronaut that we can put on board Mars 2020, but we can put this system, this terrain relative navigation system, so that the spacecraft can figure it out on its own.
I could see it being used on lunar missions, science missions, as well as human missions. Future Mars missions, of course, Mars sample return, Europa lander, landing on a comet, pretty much everywhere you want to land. You're going to want to have terrain relative navigation.
So these two stories are a kind of a glimpse of how we did the testing for the Mars 2020 lander vision system. With the field test, we were able to get a real world scenario of how well the lander vision system performed. And by going across all the different terrain and sunlight conditions and bland terrain versus really funky terrain, we thought we were getting about 30 meters performance, and that was great. That was in the family of what we expected across all of the different accuracies in environments that we could potentially see when landing at Jezero Crater. On February 18th, on the day of landing, our targeted accuracy that we wanted to pick a spot and land within it was about 60 meters. This was what we had designed to before that. Our best estimate on landing day that we thought we could get to was around 45 meters. What actually happened on landing day was that we picked a target and we got to within 5 meters of that targeted spot on the surface of Mars. So after traveling 300 million miles, after doing this test campaign that really had to Lego this testing all together between simulation, hardware testing, and flight testing, we were able to pick a target, after 300 million miles and get to it within 5 meters on the surface of Mars.
I just wanted to come back on camera just to give you an applause for that, because I know I'm the only one that can do that. But it's amazing, amazing, and it was such a moment. It was such a moment to experience and to see. Congrats to you and your team for all of that. And it all started with a flight, right? So you gotta start small to dream big, and
you gotta start small, absolutely.
And when you think about that first flight, it could be just making that simple software algorithm to know like what's a field and what's a mountain. You have to think about those kinds of things with your students to start thinking about how one day they're going to be Swati calling out the successful landing of Perseverance on Mars, right? So super inspiring stuff, Swati. We are actually now you're going to stay. We're going to bring on a whole bunch of NASA folks, and we're going to go into a Q&A. And we have another guest that's actually joining us, George, who has flown a lot of microgravity experiments, starting from space shuttle onwards to a lot of zero-G flights as well, and he's going to come on board. So at this point, why don't we go ahead and get a bunch of NASA folks on board, and while we're doing that, for everyone in our audience, this is the time where we're going to take your questions. So just load up the Q&A with all kinds of questions that you have. It could just be about anything that you're curious about at NASA. You could, whatever you want to ask, we're going to address these questions now. And then after this Q&A, we're going to dive into some education lessons that take some of these big pie-in-the-sky ideas and think about how you can get started with your students doing their very first flight experiment. So come on in. It's like the Hollywood Squares of NASA. We're bringing them in. I'm the only one that knows that, I guess. Does anyone know Hollywood Squares? Okay, all right, good. So we're going to bring some in. We've got Alejandro, we've got Niki coming in, and of course we've got Swati here. And I think we have some other folks coming in, and I am going to flip over to our chat. We've got some hellos and hi's and everything here, and I'm in the Q&A section. Okay, we are starting the Q&A section. Bear with us, we're using a new platform here. So we're starting the Q&A section. So go ahead and type your questions. And I'm gonna actually just kick off while we're getting some of our other folks on board here. I'm gonna start with a question, really for Niki and Swati first, about when you were a student, did you always think that you would work at NASA? Just curious about it. No, we've got a no and we've got a 100%. So we've got the polar opposite. Okay, so who should we start with first? Niki, why don't we start with you?
Yes, I actually grew up in a family that had no NASA background or experience, and I think they thought I was a little crazy, but completely supported me. I actually went to space camp and the whole thing, saved up all my money to go, and it's all I thought about. And was really interested. Of course, this makes me sound really old. It was before the internet existed. So trying to find information, about NASA's missions, the different types of jobs. I really just thought, I knew scientists and engineers, right? And I thought, well, maybe I want to be an inventor. I didn't know what a technologist was or what technology development was. And so I kind of stumbled into that and fell in love. But yeah, I would say definitely a space nerd from way back. Yeah.
Great. All right, Swati, how about you? And then Alejandro, we'll hear about whether you thought about ever working with NASA as well. All right, go ahead, Swati.
So I totally echo the space nerd. I was always a space nerd from as long as I can remember, but for the longest time, it didn't connect that it was a profession that I could pursue. So I was like, okay, I'll be a physician, I'll be a pediatrician, because that's, a profession that you can easily relate to as a child. You go to the doctors like, oh, they make me feel better. I can do that. It wasn't until I took my first physics class in high school, towards the end of high school, actually, that it started to dawn like, oh, okay, maybe this is what engineering is. And this seems like fun and I can do this. And started to connect the dots of, well, I really like space and physics is easy for me, so maybe I should go do that instead of, slogging over biology terms and trying to go that route. I did always love space, though. I loved space camp too when I went as a child and visiting NASA.
Also, we have some more joining. Alejandro, why don't you talk about, did you grow up thinking that you were going to collaborate with NASA and work with NASA?
So but I always had that sense of like just interest to do science. Like I think that's the common here, and the support of family, support of leaders, educators in high school. That's also, I found a role model that led me through that development of getting a career in science and guided me to that process. And I always was asking myself, okay, what else can I do? So yeah, I can, I got my degree. What else can I do? So I got my master's, and then what else can I do? So I became an educator, and then what else can I do? Well, let's do NASA, and it has been a journey. It has been very exciting to be part of this great family.
Great. All right. And now we have Kris. We have Christopher Baker, who has joined us here. A new face. We have Christopher Baker is the program executive for flight opportunities and small spacecraft technology programs. And we have Jim, a familiar face, who's come on board. And we have some of our first questions. So we're going to start. And I think this is a really good first question, which is, it's a little overwhelming, but can you break it down for us how to start with a small project? That would be great. And I think, Kris, maybe you would be a good person to start with this, because when we're thinking about NASA TechRise, we know that we're not like building a Mars rover that we're sending to Mars, but we're thinking about those first little steps. And I always tell people, as an engineer, one of the greatest skills is how to think about something big and how to think about the very first step of it, right? So when you think about microgravity, it's like, well, does it float? I mean, there's like some really basic first steps. So Kris, why don't you take that question and give maybe some examples of some small projects that you've seen on flights?
Sure. Yeah. So one of the very interesting things about the microgravity environment is when you remove that kind of dominant force of gravity that we're all used to dealing with, things behave a bit unexpected. So something as simple as you've got some water and you've got a balloon full of gas, and you let the balloon full of gas go into the water. You kind of expect the bubbles to come up. Well, in microgravity, they don't. there's no mechanism by which the heavier water stays down and the lighter gas goes up. So you get these really weird kind of two-phase flow mixing problems. And this causes all kinds of issues for technology for NASA, things as simple as refrigerators, mechanisms to separate out particulate and other things just don't work the way they work on Earth. So something as simple as a two-phase flow experiment with water and gas, that's something that professional, NASA and university and corporate researchers are spending time on microgravity flights doing. And it's pretty basic. It's a tube full of water, and you introduce gas on one end and you watch what happens. And we're still learning a lot about that. And just that, also that opportunity from the high altitude balloons being able to look down at the Earth or look up. You get 4 hours of time at an altitude there that's just exposes the sensors you might bring up there, and those could be simple as cameras, as was stated earlier, to some really interesting opportunities to get a view of the Earth that few have ever seen. So there are some really simple experiments that are still a challenge. I mean, Niki mentioned dust mitigation. We've got experiments where we've have university researchers with rocks at the bottom of a tube, and they fire a little tiny projectile into it just to carefully measure how everything moves in that microgravity environment, because we just don't have that understanding yet of how physics behaves when you remove that dominant force that we're all used to dealing with.
Great answers all around. And I should emphasize too that it's all about the education journey of feeling like I set out to do something. And even if you set that goal of, I set out to take a picture from a balloon of a certain thing, right? And at the end, you go through that journey and you have that sense of completion. That's such an education lesson right there, right? To like go through that process, to launch it. And when you launch it, You know, you don't get a second try. You guys know this at NASA, right? You launch it, you got your one shot and your one shot only. So it's all about really preparing for that moment. And I should add, we're going to talk about this later, that one of the cool things about this challenge is that all of these vehicles that are flying are sending data to these payloads. So for example, you'll get a little signal that says, oh, microgravity started. And so it's a really great way to get hands-on with coding. And we're going to go into that right after this, about how to use that trigger to make something happen. You know, maybe it just pops open something and something happens, right? So there's ways to think about it small and ways to think about it really big. So next question, is one of the objectives of the lunar exploration experiments to prep the lunar for future return missions? That's a good one for Niki, and I think that's a general question about NASA lunar exploration. Are you guys interested in doing, I guess I'm going to interpret this one, Kenza, for future return missions. I'm not thinking sample return. I'm thinking humans going back to the moon. That's how I'm going to interpret that in terms of return. So Niki, talk to us about the role of technology and getting humans back to the moon.
So what I would say firstly is we're very excited about getting humans back to the moon, but there is a lot of work and a lot of flight opportunities that we can take advantage of between now and then. So about, the question that just came up, right, about how do you start, where do you start? How I usually start is thinking about just kind of real world scenarios. And I found that students are the best ones to have these conversations with, because you sit down and you say, you know, just think about what do we need to know before the humans go? Well, I talked a lot about the regolith. There's so many questions, right? Even though we went to the moon during Apollo, we went to, you know, specific places. The lunar regolith properties are very different depending on the landing sites you go to. We've done a lot of flights where we have imagery and data of where we feel very strongly where the water would be and how to get to the water and the other consumables, but we haven't actually done that, right? So until you've actually done it, it's a theory. And so we really need to get there on the surface and test it. And so we have a lot of work to do before humans show up. And that's why I was mentioning in the suborbital flights and some of the demos we're doing there, before we do our CLPS, our commercial lunar payload services flights to the moon. Those are uncrewed flights that are starting up here very, very soon in the next year. I mentioned Prime was going, that we go before the humans go and we kind of scout out things, to be quite honest. We go and prove that we can find and collect and assess water. We go and we send these little scouts. We have these little autonomous scouts. They're so cute. And they carry payloads about the size of a bar of soap. And we did crowdsourcing challenges for those payloads to do all kinds of neat instruments and tools. And they rove around. So for example, you have the permanently shadowed regions on the moon where we think there really is water and valuable resources. Well, those areas are always going to be dangerous for humans to go down into, but we could certainly send these little scouts down with cameras and with different tools and instrumentation and check it out before the humans even arrive. So what I would say for this question and for the other one on how do you start with a small project idea is really to kind of think out those basic scenarios. Is what is that fundamental foundational information that we need? You don't want to make too many assumptions, because like Kris said, things that you just assume on Earth and you just don't even give a second thought anymore are so different with lack of gravity, right? Or less gravity. So I have found that students don't have quite the think that us adults do. So if you throw out some of these scenarios to them and really kind of say, let's break that scenario down, and where would the scout go, and what would the scout do, and what would it gather, and what kind of questions would it ask and need to know, what kind of data would we need? Those are the same things that we're thinking about now, and how to use those CLPS missions before we send humans.
Really great answer. We have a question here from Tony, which is, will the experiment need to be powered by a battery contained inside the box? If so, is there a limitation on voltage or the type of battery? Really, really great question, because it's a great segue for me to say, we're going to put the link to the website on here. And if you go to the challenge page, there are tech sheets for each of the vehicles. Boom! On cue, Kris. Look at you putting those out. There are tech sheets for each of the vehicles, and it tells you some of the specs and the limitations of what we have. But what's exciting, remember I told you that we're going to be streaming data to all of the payloads from the vehicle, as well. There's going to be power. So when you think about like, oh, I'm going to be on a 4-hour flight and it's going to be cold, and how are my batteries going to do? You're going to be able to tap into the vehicle power to be able to run those experiments. So go ahead and check out those tech sheets on the Future Engineers website. You can learn more about that. I have another great question from Tony, which is, can you please provide some of the limitations or parameters for what's possible to be done in the 4x4x8 CubeSat type module? And I think this is really just like, okay, we've got 4 inches by 4 inches. It's this size right here. Bam, bam, bam. So we've got 4 inches by 4 inches by 8 inches, and try to think like, how much can you really pack into this? And what some of you might not know is that NASA is flying satellites half this size all around you all the time right now, and they pack a lot of punch. So, there's definitely weight limitations and different limitations, but I don't know if Jim or Kris or anyone else wants to talk about how there's great things that come in small packages in spaceflight. Why don't you chime in on that? How about Jim?
Okay, sure. It's amazing what the changes that are taking place right now. And especially in the electronics field, we're seeing it in spacecraft. We never used to think that you could do valid science or technology demonstrations on something unless it was a table size or something like that. And now what we're finding is, as you said, what we call the 1U unit, 4x4x4 inch. And when we do these challenges like Honey, I Shrunk the Payload, we're finding there's a lot that can get done there and done very quickly. And so a big advantage of thinking small is it also helps you think more quickly and enable things much more quickly. So like one example we have is it's a bit bigger, maybe twice that size, is we're flying a small spacecraft to the cislunar space and to the orbit that the Gateway is planned to fly. And we said, about 2 years ago, we said, well, why don't we try to do something in a small package that gets to there and actually try out the orbit we've never actually flown in before, that the Gateway would fly. And then we also challenged Kris and his team to say, okay, we want you to do that quickly as we go through it. And so what we've done, and it's about, we started then, it was just an idea in around August or September of 2019. And we said, let's try to get there in 2 years time or something like that. And now our payload is going to be ready. And that was like a clean sheet of paper. We didn't have a contract. But we were able to get there, and by July of this year, it's going to be ready to fly, and then sometime this fall it'll probably fly. So there's lots you can do in small packages.
If you're not, if you're worried about how much space, the electronics days, you only need about this much of the box for the electronics, and the future engineers team will have some kind of tutorials available later, and a couple of workshops throughout the summer. But like Jim was saying, we're using stuff not that much bigger to go to the moon, and there's a thing about half that size flying around Mars right now on occasion. So there's a lot you can fit in there, and I think we've all been surprised by that over the past 2 years. Hopefully you will too. But that 2U package hopefully will provide you enough room to do something really cool. And we certainly think it does. So we'll look forward to seeing what you guys all come up with.
I like to think like this. I like to think, the suborbital flights are kind of a testing ground, right? You get 3 minutes of microgravity to make sure it works before you give it a lot of microgravity time, right? And I like to think about that as it's a proving ground for developing technology. But for these students, that's the end goal of this challenge, is what are you going to learn there? But it's also a proving ground for them to develop those skills to go on and do these other things. So with thinking small, I've heard the experiments as small as like putting bubble wrap in something, right? And seeing what happens when it goes up in altitude. Obviously, it's TechRise. So we're hoping you put some tech with that bubble wrap. But start thinking small and dreaming big is kind of the big idea with this. So on that note, I think we're gonna wrap up the Q&A. And we're going to go towards some of our education sessions. And as Kris mentioned, we have 2 educator workshops coming up. We have an educator workshop on July 28th. We have another one on August 11th. And the idea here is, this is all like really top level stuff. The idea is we're going to take you step by step by step with how to use a microcontroller to do something really simple, like turn on a light, to get that first idea started, so you can start thinking about projects to do with your students. And so we are going to transition now. I'm going to say goodbye to all of our wonderful speakers, except Kris, you get to stay. But all the rest of you, I just want to say thank you for being a part of this with us from the bottom of my heart. And we're going to move on to our session where we talk about our resources and tutorials. So if you go to the Future Engineers website and you scroll down, you will see there's curated links and lessons in different areas, but that's just the beginning. We're rolling out a whole bunch of tutorials about how to get hands-on with coding for the first time, and how to design for flight. And we have something really special in store for you today that we're going to give you a sneak peek of a simulator that can be used, once students get awarded. You can use this simulator even now to start tinkering around. So we're going to start first by Kris just giving us an overview of these 3 vehicles to understand really the opportunity that there is here for the different types of experiments students might think about. And then we're going to switch it over to some folks, Tanya and Arnie, to give you a little demonstration and a little overview of what is a microcontroller. So go ahead, Kris, and why don't you start with the overview of the vehicles. You're muted.
Sorry, thank you. I'm sure that's happened to most of us at least 100 times over the past 15 months, but apologies. All right, so as you heard earlier, I'm the program executive for the Flight Opportunities Program, and during our kind of regular business hours, we try to get promising technologies for space exploration, discovery, and the expansion of space commerce tested through suborbital flights with industry providers. And what we're really excited about with this challenge is we're giving students access to those same types of environments and those same NASA-sponsored commercial flights that we use for our technology development and demonstration. So as was stated earlier, there's 3 flight providers who are providing flights for this challenge. So Raven Aerostar will be providing their high altitude balloon. It's a 0 pressure balloon. It'll give about 4 hours of flight time at 70,000 feet. And during that time, the experiment will have exposure to the upper atmosphere, views of Earth, perhaps if you can look around the balloon, views of space, and for imaging and kind of remote sensing purposes. And then Up Aerospace and Blue Origin will be providing suborbital rockets. Those are the Up Aerospace Spaceloft XL and the Blue Origin New Shepard. And those flights will take experiments just past the edge of space, and they'll experience about 3 minutes of microgravity, or 0 G, as is often said, weightlessness. That will help you examine some of the effects of microgravity relative to things for space exploration, like we were just talking about a few minutes ago, in terms of when you remove that dominant force, what happens. Fundamental physics experiments get done on the International Space Station and other platforms in this way. And this helps us test out technologies that we can use for the Moon, Mars, and beyond in that environment where we've got lower gravity, and also in getting to that environment with those long duration space flights. You'll also get exposure potentially through the window to views of space. Today's session is really meant to give us all a kind of a brief overview of the elements and the experiments and an introduction to these. And next, we'll be going through this flight simulator from each of the flight providers that will give you a little bit of a feel for kind of what your payload, what your educational experiment might see. And we don't really expect students or teachers to have experience with suborbital flights. We're welcoming submissions from teams that have a great idea, but don't have the experience yet with coding or electronics, or really know what they're doing, which is totally understandable in this situation. So if selected as a winner, Future Engineers will help provide technical support as you embark on this journey. And there's going to be a series of workshops over the summer to help you get better acquainted with some of the capabilities you might leverage to do this. And you're going to get a little bit of a taste of that right now. So thank you all. And now you're muted. It happens
Okay.
to the best of us.
It happens to the best of us. All right, so I put an image of the vehicles up on the screen. So now we are going to once again, I just want to remind you that we've got this data coming from the vehicles, right? And so we can use that data to trigger something really simple. And we're going to walk through a sample experiment with that. And Tanya, our Director of K-12 Engagement at Future Engineers, is going to go over a basic overview of what is a microcontroller. I know this sounds complicated, but yet again, sign up for those workshops and you're going to be an expert. We are here with you every step of the way. And then next, we are going to also hear from Arnie Martin after that. And Arnie is a designer, an artist, and a professor of product design at Art Center College of Design. And we are going to hear from them both. So I'm going to stop sharing my screen and I'm going to go to Tanya.
Hi guys, Tanya from Future Engineers. Microcontrollers are part of everyday life and are everywhere, from your computer keyboard to microwave ovens. The electrical devices all around us rely on microcontrollers to work. Even a car can have over 65 microcontrollers in it. So you might have seen that YouTube video of the squirrel obstacle course or the glitter package. Those are made possible by microcontrollers. I have a few boards here to show you. So you see this black box right here? That is the microcontroller. And let's go to a few slides. So what is a microcontroller? Microcontrollers are programmable integrated circuits that come in many different shapes and sizes. They are essentially mini computers that can do basic math and logical computer operations. Many microcontrollers can perform millions of functions per second. I wish I could perform millions of functions per second. That would be amazing. Typically, they're used in applications that require a repetitive function, such as, but not limited to, traffic lights, the remote for your TV, high-tech devices, washer and dryers, microwaves, satellites, rockets, and more. In our modern world, microcontrollers really are all around us. So you're probably wondering, what does this have to do with NASA's TechRise Student Challenge? Well, I'm going to tell you. The TechRise Challenge is all about using science and technology to discover more about the world around us. And because microcontrollers can be programmed to do many different functions, you and your students can use them in your TechRise payload design. Maybe you want to snap a picture above the troposphere or use a sensor to record air pressure at a specific elevation. Microcontrollers can do that. And the possibilities are nearly endless. So I'm actually going to hand it off to Arnie, and he's going to actually show us how to use flight data from our flight simulator to get a microcontroller to basically trigger it to do something. Now, this flight simulator is actually available in our TechRise Challenge page, and I'll put that in the chat. So without further ado, take it away, Arnie.
Thanks, Tanya. Hi, everyone. Happy to be here. As Deanne mentioned, I'm a designer, an artist, an educator, and I've always had a kind of deep curiosity for science and engineering and technology. So as a teacher at Art Center, I developed a class for students who had never written code before to learn how to make interactive devices using a programming language called CircuitPython and microcontrollers like this one. And I guess that's just to emphasize the fact that, this is pretty accessible technology. It's really not as difficult as it may seem. And so today I'm going to show you a quick demonstration where we're going to see how this little Circuit Playground Express microcontroller can be programmed with CircuitPython and can help teachers support students who want to create science experiments that fly to the edge of space. CircuitPython is a pretty good way to do this because it was designed specifically for novice programmers to learn to write code for microcontrollers, just like the ones that Tanya just introduced. So here's the scenario. I'm going to share my slides here really quick, and I'll give you the scenario. Let's imagine that a group of students want to explore how confetti behaves in microgravity for a party in space. Well, we just heard about 2 TechRise challenge flights that will experience a short window of microgravity aboard suborbital rockets. And both of those flights with Up Aerospace and Blue Origin, as well as the high altitude balloon from Raven Aerostar, have what are called specially designed chassis that can contain experiments designed by students. Each of these chassis give you a mechanical way to mount electronics and mechanical actuation and all sorts of things inside of this container. But they also have a way to communicate with the spacecraft. So you can actually receive data from the spacecraft and then program the microcontroller to do something with it. That flight data just looks like a long series of numbers. And this is very similar to the way in which like a printer or a mouse or a keyboard communicates with a computer. And it's using something called serial data, which is just like a long string of numbers that microcontrollers can interpret and use to communicate. So to test confetti in microgravity on a suborbital rocket flight using one of these 2U chassis, we can build what is essentially a simple robot with a microcontroller as its brain. The hardware is really simple. A microcontroller like the circuit playground that you see up there, a motor controller like that companion board that kind of mounts to the microcontroller, and a servo motor to release the confetti in flight. And because we're not really in microgravity, I put a fan in there too so that we can see it move around and hopefully do something exciting for the camera, okay? Experiments like this need a way to know exactly when the flight is in microgravity to begin experimenting or collecting data. So, or in our case, to drop confetti. So in this case, what we're doing is we're looking at this and saying, how do we know, or how can we program our experiment to know exactly when we enter the conditions that we need to be in order to test our hypothesis or collect our information or collect our data? And the way that we're going to do this today is we're using flight data or telemetry. And that flight data looks a lot like this long string of numbers up here at the top. And what's happening here is that we have a basic what's called an event at the beginning of this long string of information. And then everything after the event is essentially specific information about the flight or about the rocket. So things like time, physical orientation, XYZ orientation, speed, altitude, and all kinds of other flight data. And really the program that I wrote for today, all it's doing is responding to that one thing, the event at the beginning. And each one of those events is listed here in a table. And you can see that A, B, C, D, E, F, G, H, I through M all have meaning. They all mean something from the flight computer. And our controller is just going to collect that information and respond to it. But we don't have access to a rocket today, right? So what we use instead is we use this flight simulator. And this is the flight simulator that was developed by future engineers for this challenge. And when you look at this, you can see it's a pretty simple interface. We have controls along the bottom. And we have one way on the lower left right there to connect to our simulator and to disconnect from our simulator. That's going to be over USB. We have a play pause button, a backup button, and we can also control how fast relative to real time we run this. So we're going to run our experiment at 10x, which is faster than the actual rocket flight. And then on this, we'll see the flight path of the rocket. We'll see specific events that were in that table that we just looked at, things like liftoff and main engine cutoff, capsule separation, coast start, apogee, which is when I want to drop confetti, and then the coast end, and then also, when parachutes are deployed and when we're floating safely back to Earth before touchdown. So just as an overview, we can put all of this hardware together in a chassis. And then plug that chassis into the simulator, which is basically standing in for the rocket in this case. And that simulator is gonna pipe out data, and it's gonna just send it in long strings of information, and we're going to collect it with our microcontroller. And that's gonna be what we call input. And the input to the microcontroller in this case is just the flight data. And then the output is gonna be what I've programmed the microcontroller to do when certain events happen, so that I can do things like trigger a servo, turn on a fan motor, and then also, so that we can see the data in real time, I also have another USB output here so that I can actually see the data coming back over the USB serial. And so without too much more explanation here, I think I can switch my screen over to share my whole screen. There it is. And I can show you the live simulator, which is running right here in the upper right-hand corner. So that's the same as the slide that we just saw. Hopefully on the left right here, you can see my experiment in its box, and you can see the green LEDs flashing. That's my go signal. That's telling me that this is ready to go. And then down here on the bottom right, I have a serial monitor, which is really just a way for the microcontroller to tell me what it sees. And when I press play here, it's going to take us through a simulated rocket flight. So here we are. We have liftoff. We have red lights flashing inside of the box randomly here, telling us that the engines are burning. And we are headed for space. In just a moment, we'll have main engine cutoff, and then separation, which is when the capsule becomes separate from the rocket booster. And now we're in microgravity, and in just a moment, we're going to hit apogee of the flight, right about there. And there comes the confetti blowing around inside the box. And we're now on the downswing here. We're headed back to Earth. And in just a minute, we're going to close up the hatch there and head back down to the ground. And in just a moment, we'll see parachutes deploy. We'll see some blue lights that tell us that we're floating back to Earth, and the experiment will end. So the whole point here is that this simulator will help you, along with support from future engineers, to really develop these experiments and test them and know that they're going to work on the ground before you ever get them into the rocket. And it's going to let you develop something that really works, and it's going to help you learn a lot in the process. And with that, I'm going to hand it back over to Deanne. Hi, Deanne.
Hi, amazing stuff. It's crazy because we just launched this simulator. I think Tanya said she's putting it in the chat. When you do a live demo, you're always like, okay, I hope it works. But that was amazing, Arnie. And I think they're really great. Everyone was talking earlier about how to take a simple idea and turn it into space, right? So the hypothesis is, what happens when I release a bunch of loose particles? And you think confetti, that seems completely ridiculous. We wanted confetti because it's a launch party today, but confetti's not that far off. Like if you think about what they're talking about on the moon, having to deal with dust going everywhere, and so thinking of like what hypothesis you might have for how certain things might behave in microgravity differently. So being able to drop something like that and measure it is great. But I just want to emphasize, if this seems completely bananas, if this is just like, this is so complicated, I just want to emphasize to you, you don't even have to have touched a line of code to put in a proposal idea. And we encourage you to go to our educator workshops. You can go to the Future Engineers page and sign up for those. But you really just need to put in that proposal, put in that idea, and we have dedicated team for those teams that win. We have dedicated staff that are there to have office hours and to do sessions and to do education workshops to help you guys take your students and turn that idea into reality. So this is a really good starter. Feel free to go into that simulator. Even if you don't hook up a microcontroller to it, you could just press play and just watch the cool flight events happening. And as well, if you go to the Future Engineer site, you're going to see there's other tech sheets. Like for example, if you click Raven, you'll get to the Raven simulator as well. And I should say that's just the start. We're going to have more tutorials, and we're going to integrate those simulators to even be more robust, to integrate with more maker coding skills going forward. So this is like a tease of what's to come. So thank you so much, Arnie. And now we are going to transition. It sounds like we're going to bring on George. We just talked about microgravity. George, we are going to bring you on if you are here and ready to go. I have your slides because George has experience flying microgravity experiments. And George, it's all about challenges today. I have a challenge for you. You need to do your presentation in 5 minutes or less. Are you up for the challenge?
Yeah, but you might not want me to use my slides, which is unfortunate because that's the best part.
But I have your slides, George.
Right. So just keep showing them and I'll talk over them.
Do you see this? Oh, wait, I've got so good at clicking buttons that I need to push share screen first. So hold on 1 second. And we are going to get to your slides, George, and I'm excited to hear your presentation. So here we go. Is that what you want? Did you see it?
There you go.
All right, take it away.
Yeah, so I'm a professor at the University of Louisville, previously at the University of Utah in Salt Lake City. And the word nerd was bounced around quite a bit several minutes ago, and I started out as a rocket nerd. I still am, but in the way I also became a surgical research nerd. And in fact, what we're doing right now is developing advanced healthcare, including surgical capabilities for exploration spaceflight. And that involves little parts, and that involves big parts and parts in between. And one of the advantages that I have over most people right now that are tuned in, I've spent a lot of time in microgravity that's created on the zero-G airplane. And what that's allowed me to do is part of my brain is a 1G brain and part of my brain is a 0G brain, and it knows when to flip back and forth automatically. But what that means is I kind of understand what happens in microgravity, and that helps you understand how to design your experiment. So just, try to keep that in mind as you can. A couple of things I will mention, because I've done a lot of advising student groups. In fact, I just last summer I advised several groups in a program in Canada that are doing something very much like what you're doing. It's really easy to come up with a very complicated experiment for this little payload package. Try to keep it as simple as you can, because by nature it will become more complicated. The second thing is that if you're flying on a sounding rocket like Upspace or on a suborbital spacecraft like Blue Origin, if you've never experienced extreme G's yourself, it's hard to fully appreciate how securely something needs to be fastened so that it doesn't come dislodged during the power descent or the boost phase of flight, because you don't want things to come apart then, because if they're apart then, they're not going to work when you need them in the microgravity phase. And I speak from experience. Stuff happens and you learn from it so that hopefully it doesn't happen again. But as you're developing your experiment, as you're getting the guidance from all these different workshops that they're talking about, hopefully you'll get some good insights as to how to make your payload simple and physically robust. And then the other thing I would suggest is test again to make sure that it's operating absolutely the way you need it to. Because if it doesn't operate the way you need it to in 1G, it's probably not going to operate the way you want it to in microgravity. So those are the simple words of advice that I can offer you tonight.
Thank you, thank you, thank you. All right, so George, that was a great tee up and great words of advice to go to our educator panel next. Mm-hmm. And let me find myself here. Thank you so much, George. I think advice about a lot of the experiments you see are about keeping it simple. So we're going to next bring on our educator panel. We have 3 different folks joining our educator panel. We have Liz, we have Stephen, and we have David. And I think, Liz, you're coming on too, right? We're getting you on? So, you know what? I'll go ahead and start with introductions while we get Liz on. And full disclosure here, I teed up everyone's slides, but our introduction slides. So we're just going to rock our introductions. And if you want to share like a 1 slide while you do your introduction, you're welcome to do that. But everyone here, today we're just going to talk to these educators. All of our educators here, Stephen, David, and Liz, have experience designing flight experiments with students, getting hands-on with coding and electronics with students, and particularly with NASA flights. So we have Stephen Collicott. He's professor and flight opportunities PI. Over at Purdue University, a Boilermaker with us. We have David Lockett, Albert Einstein Distinguished Educator Fellow, the most impressive title in the entire world, essentially. And David is a middle school STEM teacher, and he's doing a 1-year fellowship at NASA, and is going to speak to some of his experience before doing that fellowship as well. And last but not least, we have Liz Kennick, who is the president of Teachers in Space, who their job is to basically get teachers working with developing experiments for space. So we're excited to have you guys. I'm going to give each of you about a minute to introduce yourself and maybe some examples of what you've done, and then we're going to ask some questions. So why don't we start with you, Liz?
Okay, great. So yeah, Teachers in Space have been flying space experiments built by teachers and their students for 10 years now. We have our own balloon program. We have flown with Blue Origin, and we have flown with SpaceX. I don't know if I'm able to share these slides, but we have a lot of experience doing radiation collection experiments, data collection experiments, and as a result of the Blue Origin flight that we flew in 2019 with the Flight Experiments program, we earned our first orbital flight. So we're putting our first 3U CubeSat into space, hopefully in the coming month. It's going on the first flight of Firefly Aerospace, and that is going to be a satellite that will send its data back to Earth while it's in orbit. So if you go on our website, teachersinspace.com, you can learn how to listen, how to find that satellite and how to listen to it. And we would love to help anybody who needs help designing and building experiments for space, because that's what we love to do.
Great. And I know you mentioned satellites, so just a reminder, we're staying suborbital with this.
Yes.
One day you're going to go farther, just like Liz mentioned. Stephen, you have experience working with university students all the way down to second graders, I'm told. So I'd love to get your introduction.
Yes, certainly. Let me here. I'm happy to be here. Thank you for having me. And yeah, for 25 years, I have been, here's some pictures from that. 25 years at Purdue, I've been working with a variety of students in a variety of zero gravity experiences. The upper left there is should be of big interest here today. That was our zero gravity glow experiment with a local second grade class. My Purdue students, 2 of them there with me. We had the first K through 12 payload on Blue Origin, and all with local fundraising, and that was great fun. That was really great fun. And you see aircraft work, the lower left, one of the early Blue Origin New Shepard flights, and neutral buoyancy lab in the upper right. And believe it or not, those 4 guys in red polo shirts are actually high school students, and that's the rocket they built. We were to launch a payload on that. So I've been doing a lot, and I'm just really excited that future engineers have put this program together. And teachers, I encourage you and echo what George said about try to keep it simple. I would just add the big impact you're going to have is not really the data from the payload, but your impact on the students' lives and their futures. And so, yeah, charge ahead, do great work.
All right, and next we're going to go to David. Why don't you give us a little introduction, and we'll have time for just like, a couple questions, and then we're gonna wrap it up soon. Go ahead, David.
Hey, thank you for having me, David Lockett. Yeah. Hey, I'm an Albert Einstein Fellow this year, serving at the Office of NASA STEM Engagement. I'm a computer science and STEM teacher, and in our classroom, we worked on a variety of projects. And working on these particular projects, I'm going to share my screen. These projects were projects that allow students to learn more about meteorology and how NASA takes different variables into account to perform missions. In these different projects that students worked on, they could plan efficiently and they could carry out balloon launches. Some of the photos that you're looking at now, students worked in various groups and were assigned different positions that are similar to those used by NASA, like flight director, safety officer, payload integration, launch operations, in meteorology. In these different projects, students correlated the behavior of their experiments to draw possible conclusions. So just give you an idea of some of the projects that we worked on throughout the classroom.
Awesome stuff. So I have, I think my big question is, how do you start? When you're trying to do something that seems this ambitious, right? How do you start with your students? And David, I'm going to start with you on that.
How do we start? I start by, piquing my students' interest, asking different questions. You like space? What do you like about space? What projects can we look at in order to, explore? How can we learn a little bit more about the natural world around us? So from there, we research and then we go into different aspects of learning.
Great. Now, Liz, Stephen, do you guys have any tidbits about how do you start?
Well, for us, we always start with what are the questions? What do you want to know? And so once they have brainstormed some questions, things they would like to find out, we do a little research, what is already being studied, what experiments have people done, and then we look for a testable question, and then we choose what is the right type of flight, because it depends on whether you want something that gets up quickly and comes down quickly and has exposure to the atmosphere, which is good for a balloon or a glider, or whether you need something that's going to stay in space for a while, in which case you might prefer to do something that's orbital, or you might sometimes just want to get it up on a rocket and see whether it can exist, whether it can survive being launched and brought back. So it depends on what you're trying to test.
How about you, Stephen?
Yeah, I would agree with what both David and Liz said. My take on that is, the students' creativity, and I'm talking the K through 12 now, not the ones I get at Purdue who've already demonstrated they're fascinated by space and don't want to do anything else in their life. But get them thinking and get them talking about what do they want to see, I think is what Liz said, or what do they want to know? What would you like to see happen with the younger students? The things going on around you in everyday life, how do they change when you go into space flight? And whether that's machinery working or whether that's astronaut lives or senses or what have you, certainly start with a really broad, wide open aperture there and just get all the ideas you can.
Really great stuff. So I want to make sure we get to Kris. So I am going to do this. We're going to go to Kris and we're going to wrap it up for this broadcast. But if anyone has any questions, feel free to ask them in the chat to our panelists, Stephen, Liz, and David. And I hope you guys can answer any of their questions that they have. And thank you so much. I think you're just illustrating the different types of experiments and things that students can consider for space. And I guess give me like a really Twitter short answer of what does it feel like when that experiment finally launches? Well, how about each of you take that real quick?
Launch is easy. It's when you're waiting to get it back and you're nervous about getting the data. That's the hard part.
That's the thing. And I think the most exciting thing for us about our Blue Origin flight was we went to lunch, we came back from lunch and they said, here's your cube. We got the cube and the data back the same day, which is what happens when we do a balloon flight. But to get an actual space flight back and the data right there, I pulled the chip, I downloaded it, I emailed it to my teacher whose class designed it, and he sent me back a chart, right? We had an
amazing
presentation the same day.
And David, you, Twitter length. I know you're active on Twitter.
Hey, definitely have that growth mindset. Don't be afraid to fail, try and succeed.
Awesome. Thank you,
yes.
thank you. I'm going to say goodbye to you guys, and we're going to bring on Kris for our closing remarks from NASA, and we're gonna wrap it up here with our final remarks. So come on, Kris Brown. Thank you so much to our panelists. All right, and last but not least, we have Kris, who is a Deputy Associate Administrator at NASA's Office of STEM Engagement. A big fan, I'm a big fan of yours, Kris, and I just love for you to wrap it up for us with some closing remarks. Thank you so much for joining us.
Great, Deanne. Thanks so much. And hi, everyone. I'm thrilled to be with you all to help close out this evening's event. First of all, I want to extend my heartfelt thanks to all of our speakers for sharing their wisdom and experiences with us. It has been such an informative and enjoyable event, and it's very exciting for us to consider the many possibilities we have in front of us. I'm thrilled to serve as Deputy Associate Administrator for STEM Engagement at NASA. Our work encompasses a broad and diverse set of programs, activities, and opportunities dedicated to inspiring, engaging, and educating students, as well as supporting educators and educational institutions. And our community is comprised of a stellar and dedicated group of people who are passionate about developing our next generation of scientists, engineers, technologists, mathematicians, and explorers. As an engineer who's now hit my third decade working at NASA, I've been fortunate to have many memorable and life-changing experiences throughout my career. I've worked on projects ranging from designing, building, and testing space and Earth science missions and spacecraft, to leading the development and operations of a mission design center, to leading the creation of future engineering design environments and tools, to running a systems engineering organization, and more. But this job, playing a role in shaping the lives of students, is truly an honor and a privilege. In NASA STEM Engagement, we aim to meet students where they are. And certainly that principle has been central to our work with students during this unprecedented time over the past year. We offer compelling and exciting student learning opportunities tied with the truly out-of-this-world technical work we do at NASA in space technology, aeronautics, human exploration, and science. These opportunities range from internships to student challenges and competitions, to research grants and fellowships, and more. and we deliberately work with educators, institutions, and partners to magnify our reach and impact. Ultimately, our aim is to build a diverse future STEM workforce, and we are laser focused on attracting students to STEM through a NASA lens, as well as enabling students to contribute to our work here on Earth and in space through unique early learning opportunities. To do our work in STEM engagement at NASA, we know that in so many ways, our success depends on you, dedicated teachers and educators. You can bring NASA into your classrooms. You can engage your students in one of our 7 Artemis student challenges, teach them about our home planet Earth and the universe with one of our education toolkits, join a NASA educator workshop, and discover resources through exploring the NASA Educator Professional Development Collaborative. To be part of our educator community, you can sign up for NASA Express, our weekly newsletter that features upcoming opportunities. We have over 50,000 subscribers, but we need more. To learn more, visit stem.nasa.gov. At NASA, we stand with you as you continue to guide students. You bring sparks of inspiration to our next generation of explorers every day. I grew up in a small rural town in Pennsylvania and was the first person in my family to go to college. I learned firsthand the power of education and its potential in propelling people on paths toward fulfilled lives and using education as a solid foundation in finding their life's work. Given my background and where I came from, it's mind-boggling that I could eventually end up here where I am today. There was little opportunity where I grew up. Educational programs to learn outside the classroom were few, but thanks to teachers who inspired and guided me, particularly math and science teachers, I ended up studying engineering and started on a path to a successful career in STEM. Students today in our ever-expanding digital world have more at their fingertips than ever before, and certainly more than I did. But they can't go it alone. STEM pathways are not solo endeavors. We know that working in STEM is a team effort. We all need to play our roles on the team in this larger national STEM ecosystem. We have the opportunity to inspire and engage students through compelling and exciting learning opportunities like TechRise. And we must continue to work diligently to address digital and socioeconomic divides and commit to broadening student participation to ensure diversity, equity, and inclusion in STEM fields. While we've made much progress, we have so much more to do. Thank you all for your contributions in shaping the next generation, and particularly for your dedication in helping us build the future STEM workforce. At NASA, we hope you are as excited as we are about TechRise. It is an outstanding example of those valuable hands-on learning experiences that can help students discover their talents and interests and their abilities to do truly amazing things. Our hope is that you will share TechRise broadly with your students and colleagues. And I'd like to encourage you all to join us again in July or August for one of 2 NASA TechRise Educator Summer Workshops, during which we will dive into the basics of electronics, coding, and designing for flight. For more information, visit futureengineers.org/NASA TechRise. Thanks again to all of you for joining us, and thanks to the Department of Education for inviting NASA to participate in tonight's program. And now I'd like to encourage you to stay as we transition to the official kickoff of the 2021 Ed Games Expo. It is my distinct privilege to introduce the Secretary of Education, Miguel Cardona.
Thank you so much, Kris. So that is the end of our NASA TechRise Student Challenge official kickoff event. We hope you have an amazing, amazing summer. That's the end of our broadcast, and we are putting the YouTube link where you can continue on your Ed Games Expo journey, and you can watch the kickoff for the Ed Games Expo. So thank you everyone for being a part of this. Thank you, Kris, for your closing remarks. And please go to the website, pre-register. We'll tell you when all these new great resources come available. Sign up for one of our workshops July 28th or August 11th. And thank you again, and have a wonderful evening. Bye-bye, everyone.